Try doing it now.
It's saying screen broadcast. Is it visible? Hello?
Yes, 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 screen is visible.
Okay.
Your voice is not coming. You are speaking, Rahul.
Okay, so I'm saying, can you please somehow take care of this part, because I'm able to see some sort of screen from my computer, but this is blocking your presentation. Yeah, this one. Can you somehow manage it or cancel it maybe? Because I can
Maybe
see plus and minus.
yeah,
Now. Yeah,
I
now it's fine.
minimized
Now
it.
it's fine.
Now it's not there. No?
This is still coming.
Shit. Whenever
Or
I'm choosing the keynote, it's coming at me.
Or maybe then you can yeah.
It's
Fine,
gone.
fine, fine.
It's
Very
gone.
good, very
Now
good.
it's gone. So good evening, everyone, and sorry for inconvenience again and again. I have postponed it. So today I'm going to talk about some magnetic resonance techniques. In previous talks, I have talked about one technique only. So today I want to talk about two more. So there are actually multiple resonance techniques. So the outline will be, I will give a very small introduction, about the techniques. Then I will talk about the number of techniques, their name. Then nuclear magnetic resonance techniques. EPR I have talked about previously, so I will skip it. And I will talk about Mossberg spectroscopy and muon spin rotation, and I will talk about in the next talk. And I will try to explain in a very simple way today NMR and Mossberg spectroscopy. So whenever we are trying to study the local environment of our atom or nuclei or the electronic structure or the arrangement, we see how they are behaving to the different crystal fields. But not only crystal fields, there are different other phenomena also, like spin orbit coupling and the hyperfine interaction with the nucleus. They all play their role whenever we are studying the actual electronic structure. So if we want to study the proper our system, or imagine we need only a particular idea, so we do different spectroscopy so that it will be useful for a different purposes. So there are different techniques. We use a nuclear magnetic resonance, NMR, EPR, or ESR, electron spin resonance. There is Mossberg spectroscopy, muon spin rotations. All these spectroscopy can give you a particular idea. They are being used for a different purposes, like NMR, or we can say in the medical field we use MRI. We do MRI to see how our brain images are there. We can get the idea about how they are reacting to the different homogeneous magnetic field. Mossberg spectroscopy, chemical chemist and the different group of the chemist use so that they can check their different radicals, how they are behaving. Muon spin rotations have its ability different from the neutron and the electron that I will talk about the next talk. So first I will talk about the nuclear magnetic resonance, and before diving into the resonance, I will give some idea that when we talk about the nuclei, we have neutrons and protons. Neutron doesn't have the charge, but proton have charge as well as a spin. And if we consider that nuclei is spinning and it's moving, so according to electromagnetic theory or classical electromagnetic theory, if a charge is moving, it has magnetic movement, then it can produce magnetic field, or we can say that it can behave as a magnet. So we can say that our nuclei will behave as a tiny magnet. And if we put our tiny magnet, which can have a nuclear spin, we can denote some value according to the number of protons it is having. So if we apply a large magnetic field, that tiny magnet will orient in a particular direction, and it has a number of orientation which can we give the value of ml, and nuclear spin can have integer value or the half integer value. So integer value we can have 1, 2, 0, 1, 2, 3 like that, and half integer value half, 3 by 2, 5 by 2. That will depend how many number of nucleons are there in your nuclei. So number of orientation we can calculate with the help of formula 2i plus 1. So if you have I half, you can calculate 2i plus 1. If you have integer value, you can calculate I plus 1. So if we have a sample which is having a nuclei which is NMR active, I will tell how NMR active and inactive we can get. And if we put in a very high magnetic field, in a oscillating magnetic field actually, and we can generate appropriate frequency, that energy can be absorbed by the sample, and that nuclei will start processing in that magnetic field. So I have taken an example of ethanol molecule, and if you see that molecule, we have three different ligands, CS3, CS2, and OH. And if we think about the position of the proton or the H atom in that particular system, the H corresponding to OH has a different environment than the H on the CS2 ligands and the CS3 ligand. So the environment of the system, whatever nuclei you want to study, the environment around that nuclei will also affect the effective magnetic field, whatever we are putting on the system. So if we put a magnetic field around the nuclei, it will start precessing, and that precession, the frequency of the precession will be directly proportional to the effective magnetic field. Not just the magnetic field which we are applying, but the effective magnetic field which is around that nuclei. So this is a simple example of ethanol. We have talked about that the environment is different. So imagine the number of electrons, one side is more. So like if we are talking about the OH side, there are less number of electrons, the electron density is very high towards the CS3 side. So the electron shielding is more towards the CS3 side. So the precession is slow, it's less. And if we talk about the less shielding side, the precession will be very high. So the frequency of the precession is actually reacting or actually depending on the effective magnetic field, on the magnetic field you have put, and the magnetic field which is actually shielded by the electrons or whatever environment you are putting on. So the frequency of radiation, the radio frequency, whatever you are putting. So in the past lecture, we have studied that in ESR, we use microwave range of the frequency, and we calculated that why we are using the microwave frequency. Similarly, here we are using radio frequency range, and the magnetic field will oscillate in the radio frequency range. So frequency of the radiation, which will be absorbed by the sample, that will depend on the three major things. The first is what type of nucleus we are studying. It can be 1H or 13C, and different nuclei we can study. The chemical environment, we have seen already that the chemical environment can be different. The third thing is a special location of the sample in the magnetic field. That this is actually a medical point of view, that whenever the magnetic field is inhomogeneous, the location of the nuclei will also behave differently, because the magnetic field is not homogeneous. So not only H1, we can study 13C, 15N, 19F, 31P, different nuclei we can study, and all of them are NMR active. So for NMR active, we are seeing that if we see clearly, this is 1H, 13, 15, 19, 31, all of them are odd, none of them are even. So we are taking NMR active when the atomic number and the atomic mass number or the nucleons, they cannot be both even. If they will be both even, it will be NMR inactive. For example, if we take 6C12, then it will not show any NMR signals because it is NMR active. So we should take a system or the nucleus which is NMR active. So we can compare the NMR spectroscopy with the infrared spectroscopy in view of that whatever transition is induced. Yes.
Can I ask a question? So let's say you have a molecule. So I don't know whether it's possible to make such a molecule or not. So let's say you take the example of C2H6, okay? And one carbon is carbon 13, one carbon is carbon 12. So will the
Yes, sir.
environment of the two hydrogen atoms that are there on the two carbons will be different? So first question. And second question, will it still be NMR active?
So if according to my knowledge, sir, because I don't know, because I have not done the experiment, if we will do the measurements, so you said one is C12, one is C13, right?
Yes.
So maybe whenever we are doing the NMR measurement, we will get the signals or the data from the C13, but we may not get the signals from the C2.
Okay. And do you only get this signal for the hydrogen atom?
No, sir. Means whatever NMR actives are there, like C13,
Okay, fine.
whatever examples I have given. I have given ethanol example because that generally they give whenever they are teaching. Because
Mhm.
we see the proton environment generally the same. We can see what type of protons are there around the system.
Okay, so if I understand it correctly, you said that the carbon atom which is C13 may give
Yes.
magnetic resonance, whatever the signal, but it may not be given by.
C12 will.
Okay,
C12.
okay. So
Yes.
what? So maybe if
Because if we see the nuclear spin value I,
Mhm.
that I value will be 0 for 6C12.
Uh-huh.
So that will be NMR inactive.
Acha, so can I ask one more question? So will you also show us how to read those graphs? Because I've seen them at many places, but I don't know how to read those graphs or those plots.
Which graphs?
Because you get some plots in the NMR experiment, some sorts of peaks there are there. So will you
Okay.
explain how to read them?
I have made one animation where I have shown the peaks and their splitting.
Okay.
So which splitting is happening because of different proton environment, and the shift is there because of their different chemical shift.
Okay. So
Okay.
you cannot really identify the kind of elements you have, but you only identify different types of atoms in a given molecule. Is that correct?
Actually, yes, correct. We can just get what type of, if we have similar type of ligands, and we know that already these type of protons or the carbon atoms are there, and we just want to know that where they are present. We already know the system, but we want to know their locations. That we can do with the NMR.
Oh, so you cannot really identify different elements through it, like whether the molecule has carbon, hydrogen, sulfur, oxygen, etc., or not.
So if my knowledge is correct, we don't.
Okay.
But Prakash sir can tell exactly, because we just tell the environment according to how they are shielding and how they are splitting according to the NMR active nucleus.
Rahul bhai,
Prakash sir.
can please tell the question?
So my question is, I know one method, something said spectroscopy, something like that. So maybe gas spectroscopy, or if I'm telling that correctly. So that can identify, let's say you give it some sort of molecule. Let's say it will be
Okay.
ethanol. Okay. So it
Okay.
will identify the molecule for you, that it has this many number of carbon atoms, hydrogen atoms, oxygen atoms, so that you can know which molecule you put or gave it to. Okay. So my question is whether it's also possible using NMR technique.
Exact molecule you may not get, but it will give you the active nucleus from where you are getting the signal from. But it cannot exactly give you the molecule, because in order to get the complete structure of molecule, you need to have an idea about the electronic structure. So that sort of information this will not give, because that information will come from ESR.
Okay. So if I were to take the example of ethanol again, so as you said that there are three different types of hydrogen. One is with the hydroxyl group, the methyl
CS2
CH3,
group
and
and CS3 group.
yeah. So NMR can give me the idea that it will have three different sorts of hydrogen in it, but other than that, it will not give me any other information.
No. What Nikhil is saying, it is from ethanol, because he has I think he has taken it as an example. But as I know, it will only give you an idea about the what sort of active nuclei are present and responding to the instrument we have devised or put them under. Apart from that, it will not tell much, because let's suppose carbon.
Mm-hmm.
You have raised a very beautiful question. Let's say carbon.
Mm-hmm.
Carbon can actually exhibit in many types of polytypes, like say graphene, graphite, and
Carbon.
amorphous carbon. So it will only tell you what carbon it is, carbon in what form.
Mm-hmm.
Apart from that, it will not tell much.
Okay.
So you need complementary technique. You need complementary technique to have complete information.
Okay. Okay.
So I think you are talking about gas technology, gas spectroscopy might be inductively coupled plasma. I think you are talking about that.
I mean, I'm not able to recall the name of that technique exactly, but so something like spectroscopy or spectrographs. I don't remember the exact name. So it can give you
Let's
the molecular structure.
okay. Let's suppose another thing. I can X-ray photoelectron spectroscopy. This is another spectroscopic technique.
Okay.
So there actually what you do, we do actually expose the element to the X-ray photoelectron spectroscopy, and depending upon the band gap of the electron or energy level, the corresponding electron get excited, and during the excitation, we got the corresponding spectra at a
Mm-hmm.
particular wave number or that energy value, so to say. So it will only tell you actually that particular element actually in what uh, which bond actually it is favoring in that corresponding substance or material under investigation. Let's suppose the nitrogen, you can have nitrogen N2, it is triple bond. You can have a CO2 double bond, C and O, isn't it? So there are different molecule which will give you the different bonding, single bond, double bond, triple bond, and
Okay.
depending upon, yes, depending upon that bond strength, it will have a different energy of excitation and a de-excitation.
Mm-hmm.
It can give that amount of information.
Okay. Whether the
Actually,
bonds are double, triple, or single bonds.
yes. So,
Okay.
but it will not give you information with whom or with what element it has made that number of bonds.
Okay. Okay. Got it. Got it. Got it. Thank you. Thank you, Gyanti bhai.
Okay. So I think partially I have at least helped.
Thank you so much. Yes. Yes. You have.
Okay. Thank you.
Sir,
Nikhil,
whatever.
proceed, please.
Yes, sir.
Tell me.
No, Rahul Bhaiya is talking about some spectroscopy which tells about the elements or it tells about the system, the whole molecule.
No, he said, suppose we put the ethanol molecule under
No. Sir
investigation.
said, sir has studied some gas spectroscopy or something.
No, I've heard about it. I've heard there's some technique. So let's say if you give it, or if you give it, let's say ethanol C2H5OH. So then it can give you that it has 3 number of carbon atoms. This is what I got from that. Do we have such a
Yes,
technique?
that technique
Yes,
is there.
actually, it is written that they use gas chromatography or mass spectrometry.
Mass spectrometer. Yes, I was talking about mass spectrometer. Yes.
Yes.
They said they use it to check drugs and all in airport security and all.
Yes, I was talking about mass spectrometer.
Okay, mass
Yes,
spectrometry.
because there you will get the mass number of every individual element.
Okay.
Actually, in NMR, we see what is the nuclear spin value I, which is actually whatever additional nucleon we are having nuclei rather than the what should I say fulfilled nuclei. So we are actually either studying the environment of the whatever NMR active nuclei is there, or the environment of the electrons around it. So we cannot get exactly element from that.
Okay. Got it.
So two scientists, Edward Purcell and Felix Bloch, actually they can be called the godfather of NMR. In 1946, they gave this NMR spectroscopy. They also got Nobel Prize in 1952 just because of their contribution in that field.
Nikhil, may sorry to interrupt. May I ask for a small clarification?
Yes.
So E.g., this Professor Edward Purcell, who has written a book on electrodynamics from Berkeley.
Yes, he has done, I think, PhD from Harvard and has written the book. And
Okay. So yeah,
Felix Bosch, I think he was the first managing director of CERN also.
director of CERN. Yeah.
Later on, means just
Okay.
after the Nobel Prize winning, I think 1954, 54 or 55, he was made the Director General of the CERN.
Yes, first director.
So I think as a person, Bloch was bigger personality rather than Edward at that time. So these both were called the godfather of the NMR, and later on, because of the utility of that NMR spectroscopy, they were awarded Nobel Prize in 1952. And Bloch actually started working during World War time for studying the nuclear magnetic spectrum and their responses. And later on, he combined with the Purcell, he gave that spectroscopy. So if we think about the mechanism of the NMR, the nuclear spins, they interact with the effective magnetic field, and that effective magnetic field is actually made up of three components. So the first component is an external magnetic field, which we are putting on the sample. This is homogeneous and in the fixed direction. So if we compare with the APR spectrum, in the APR spectrum also we put a magnetic field which is from the which is having a fixed value, and then we give microwave frequency to excite, and we see the absorption and the different spectra. In case of NMR, we have an external magnetic field. This is fixed, homogeneous, and a fixed direction. Then there is a radio frequency, the third point, which is actually oscillating magnetic field. And there is a second part also, which is actually an internal magnetic field, which is due to the presence of other nuclear spins. So if we go to the technical part, if we write the Zeeman Hamiltonian for a single spin in presence of magnetic field 1 and 3, we can write as a minus mu dot h, where ht is the effective magnetic field, and h naught g is the first part, the external magnetic field, which is in z direction, and the h1 cos omega t x direction, this is in x direction. This is the part of the radio frequency magnetic field. But there is one also specific use of the second part. If we are doing the MRI, we generally take the circularly polarized magnetic field, which is having X part and the Y part both, so that they can extract more data by changing and using the X component and the Y component, whatever more useful for them. They don't want the to do the measurement again and again because of some constraint in the medical field. So they use circularly polarized light, and they get the data whatever they want by changing the direction of the radio frequency magnetic field. Why I have not used the second part of the magnetic field, which is internal magnetic field? Because most of the time that part is very less, or either it's very less, or we can include it in the first part. Most of the time they include it in the first part, and they check the contribution from the system already, and that part they take as a constant value, or they can contribute in the separate contribution. So here I have given an animation of the ethanol molecule. So in the bottom, this is OH, and the right side is the CS2, and the left side is the CS3 ligand. In the CS3 ligand, one nuclei is not visible. I have shown only one nuclear spin, but actually every hydrogen atom has a nuclear spin, which I have not shown, but all of them have. So if we see, if we put a radio frequency, then OH will give a signal in the time domain, similarly CS3, similarly CS2, and then we will do the Fourier transform. In the frequency domain, we will get three signals. We will check the chemical shift, and according to the different environment, they will split. The CS2 will split into 4 parts, and the CS3 will split into the 3 parts. Because if you see their environment, broadly we can see the environment. CS2 has 3 protons, or the nuclear active NMR active protons, 3 CS3 side and 1 OH side, which has 4 splitting. In CS3 we have 3 splitting. Though the intensity of the peak, the chemical shift of the peak, and the splitting, all 3 factors we study, then we give the idea about what environment is actually we having in the system. So that's how we do the NMR and we get the idea about our system. Now I will talk about the Mosber spectroscopy, which we also call gamma ray spectroscopy, because we use gamma rays as a absorption, as a energy absorption, which we are using. And we study the transition between the excited states and the ground states. And that we can also do only on the Mosber active nucleus, which is having the nuclear spin I greater than 0. And for that, the ground state and the excited state should have different I values. So here, the simple principle is we have a radioactive source, imagine X, which is having Z atomic number and A atomic mass. If it will capture one electron, it will get a Y, which is having one less atomic number and similar atomic mass. So generally we use cobalt 57. It will capture one electron and we get a excited iron atom, system, which is having a same atomic number. But that is in excited state, so it will lose gamma ray and it will come to the ground state. According to my point of view, there are very specific systems only we can study through this spectroscopy. And these 5 are there: iron, tin, iodine, EU, and AU. So these systems we can study through this spectroscopy. And out of these 5, 90 to 80% spectroscopy they do in iron and tin. And the reason is we need a radioactive or unstable source. In case of iron, we use cobalt 57. In case of tin, I think we use indium 119. So because of that restrictions, they generally do this spectroscopy in these two systems, which systems have either iron or tin as a metal, what should I say, metal center. So how does this actually happen? So whenever the iron will get the gamma ray, it will be in excited state. It will lose one 14.4 keV energy gamma ray, and it will come to the ground state. So excited state is in 5/2 nuclear spin state, and the ground state is in I 1/2. So one condition is actually already fulfilled. That gamma ray will be absorbed by the same iron atom, the different iron atom, but both are iron only, and it will absorb the gamma ray and it will go to the excited state. But there is a catch here, and that catch is actually recoiling of the sample system. Whatever sample we are doing the measurement, that sample will get some recoil, and because of that recoil, whatever energy is gamma ray is having, that energy will also used in recoiling. So we need gamma ray with slightly higher energy than the resonance energy of the sample system. So if we need E energy for the resonance, the gamma ray energy should be more than it, and it should be with the same amount as the resonance, as the recoil energy. But in case of the spectroscopy, we need recoiling as less as possible. So for that reason, either we use the crystalline solids or we keep our nucleus, whatever we are studying, in a very bound state. So if it is bound, the recoiling will be really very less, and whatever energy we need will be very slightly different from the resonance energy. So we know that we are using the source as a cobalt, and we are getting the iron in the excited state, and the sample is also iron. So we know that there will not be a very much difference between the E gamma and the E resonance. But there is a slight difference, and that slight difference we will achieve by the Doppler effect. How Doppler effect is taking place here? So imagine the cobalt atom. Cobalt has captured
Nikhil, you are not audible.
Hello.
Okay.
Am I audible now, sir?
Yes, yes, you are. Actually, there was problem
Okay.
from my side.
Okay, no issue. So if we take a random value that the emitting gamma ray has a energy of 14 keV, but the required energy is 2 keV. So till the energy of the gamma ray is not 16 keV or more than that, it will not be absorbed by the sample nucleus. So what do? We use the Doppler effect. That energy of the required energy is not that much. It's not 2 keV. I have just taken an example. So how we achieve that extra energy? We use the Doppler effect. If the observer and the source, they are moving towards each other, the frequency will increase. It means if we convert that frequency into the energy will increase. It means whatever energy the sample is seeing, it will increase by some amount. If that amount is equals to the required energy, that absorption will take place. So I have, and that speed of the source, they directly use as a chemical shift. Whenever they plot that spectra, they use that speed of source as a chemical shift, and the intensity of the light, intensity of the gamma ray, which is being absorbed in the y-axis. So I have make a table for that so that we can understand it easily. So imagine I have slowly increased the speed of the source from 0 to 25 mm per second, and the energy of the gamma ray is changing according to the speed when the sample is in stable condition. It means the observer is static position and the source is moving towards the sample. So energy is slowly increasing, and as soon as it has become 20 mm per second, the energy is 16 keV now, and it will be absorbed by the sample, and the intensity which is being observed from the detector, it will suddenly drop to 30% because a huge amount of the gamma rays have been absorbed from the sample. So the whatever gamma rays are reaching to the detector, the intensity will decrease. So we will get one signal. We will get one signal at a particular speed. Here, 20 mm per second, sudden drop will be there in the intensity, and we will see one signal. That Doppler shift we can calculate, which depends on the frequency of the radio frequency and the speed of the source and the speed of the light. So this is the simple diagram I have shown where we can see there is a source, it's moving towards the sample. That gamma ray which that sample is seeing or the observing, that frequency will change according to the speed. At the speed where the energy is enough to overcome the required energy, it will absorb the gamma ray and we will see the signal from the detector. So how many numbers of signals will be there? That depends on the nucleus and the electric field gradient which is there. If the electric field gradient is 0, the electric quadrupole will be 0. If the electric field gradient is non-zero, the electric quadrupole is non-zero. I will explain what is the meaning of that. So there will be no splitting in the signal when the electric field gradient is 0, either in ground state or in the excited state. In both cases, if there is no gradient, no splitting. Splitting will be there if field gradient is present. So there are two symmetry which are present in case of any system. The first is electronic symmetry and the other is ligand symmetry. Electronic symmetry means imagine we have T2G state and EG state. In T2G state we have either 0 electron, 3 electrons or 6 electrons. So either they are totally vacant or half filled or full filled. In these three cases, there is a electronic symmetry. It means there is no field gradient. In EG case, either 0, 2 or 4. In these cases, there is a symmetry and there is no field gradient. The other is ligand symmetry. That M is actually metal center and L are the ligands like CS3, CS2, OH, whatever around the system. Imagine all these ligands are same. M is CS3 or and these are OH, 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 OH. All the 6 are OH. Then there is a ligand symmetry and there will be no splitting. We will get only one signal. Imagine one ligand is different. One is CN or CS3 or something else. Then the field gradient will happen and we will see there is a splitting according to the situation, either in excited state or ground state, whatever field gradient is present. For example, one example I will give. These are the number of splitting depends on the I value. if we are talking about the excited state or the ground state. So imagine we have excited state I value 3/2 and the ground state value is 1/2. For this example, ground state, there is no field gradient, so it will not split. It has two degenerate values, plus half, minus half are there, but there is only one energy state. But because the field gradient is present in the excited state, that 3/2 will split into 3/2 and 1/2. So we have two signals. According to the selection rules, we have two signals in that scenario. But in the second example, imagine we have a system of FeCN6 4 minus. In that condition, Fe has D6, T2G has 6 electrons, and Eg has 0. So electronic symmetry is present. According to the ligand symmetry, all the ligands are same, CN6. So the ligand symmetry is also there. So excited state as well as ground state both has no field gradient. It means there can be 4 splitting in the excited state, 2 splitting in the ground state, but they will not happen. There will be no splitting happen because of the symmetry presence. So we will see only one signal. It means according to the signal, according to their shift, we can check what is the environment is there, if the ligands are symmetric, if the ligands are same, if the our metal center is in excited state, is in a condition where the electronic symmetry is not there. That data we can get from the number of signals, from their intensity, and the chemical shift or the speed of the source. So that's all for today. And in the next talk, I will talk about muon spin rotation. Thank you.